A pH buffer is a solution that resists changes to pH. It's made up of two parts, a weak acid and a salt containing its conjugate base. The way they work is simple neutralization chemistry. Any hydroxide that's introduced to the solution will be neutralized by the weak acid, while any hydronium is neutralized by the conjugate base. You can calculate the pH of a buffer solution using the Henderson-Hasselbalch equation, which says that the pH should be equal to the weak acid's pKa plus the log of the conjugate base's concentration over the weak acid's concentration. For example, let's say we have a 1 molar solution of nitrous acid and a 1.3 molar solution of nitrite. The Ka of nitrous acid is 4.5 times 10 to the negative 4. Taking the negative log of that gives a pKa of 3.3. Plugging this pKa and the two concentrations into the Henderson-Hasselbalch equation gives us a pH of 3.4. Now let's imagine making a liter of this buffer and adding 0.2 moles of hydroxide to it. And to keep things simple, we'll assume the volume stays 1 liter. The hydroxide will be neutralized by the nitrous acid, producing water and nitrite. We started with 1 mole of our weak acid and 1.3 moles of nitrite. The stoichiometry is all 1 to 1, so after adding 0.2 moles of hydroxide, it takes that same amount of acid to neutralize it, which also produces an equal amount of nitrite. This means that after the hydroxide is neutralized, we end up with 0.8 moles of nitrous acid and 1.5 moles of nitrite. If we plug these new concentrations into the Henderson-Hasselbalch equation, we get a new pH of 3.8. So our buffer solution started out with a pH of 3.4, and after adding the hydroxide, the pH changed to 3.8. So adding the base did cause an increase in pH, but only a little. Especially if you compare adding the same amount of hydroxide to a 1 liter solution of just water. With nothing to neutralize it, the hydroxide concentration becomes 0.2 molar. The calculated pOH would then be 0.7, which converts to a pH of 13.3. So adding the hydroxide to our buffer solution caused an increase of only 0.4 pH units. But if it had been pure water, the pH would have shot up by 6.5. Now let's take another liter of our original buffer solution and this time add 0.2 moles of hydronium to it. Again, keeping the volume at 1 liter the whole time for simplicity's sake. This time it's the nitrite that's doing the neutralizing, making our products water and nitrous acid. We start with 1.3 moles of nitrite and 1 mole of nitrous acid. But after we introduce the hydronium to the solution, we'll need 0.2 moles of nitrite to neutralize it, which in turn increases the nitrous acid by the same amount. This means that in the end we have 1.1 moles of nitrite and 1.2 moles of nitrous acid. Plugging these new concentrations into our Henderson-Hasselbalch equation gives us a new pH of 3.3. If we add that same amount of hydronium to a 1 liter solution of water, the hydronium concentration would become 0.2 molar, giving us a pH of 0.7. So similar to what we saw when we added hydroxide, adding hydronium to our buffer solution does cause the pH to drop, but it doesn't seem like a real significant drop, especially if you had done the same thing to simply water.